So for the part one, there have a few parts here. For the first part is introduction of NMR. And we know that NMR is a powerful analytical techniques. Every university, every researcher need to have this at least one. So the use is characterizations of organic molecules by identify the carbon hydrogen frameworks, the usually compound that exists in organic compounds. And there are two types common in NMR spectroscopy. The first one is a proton NMR. It's determine the types of the number of proton atoms in molecules. And the carbon-13 is usually to determine the type of carbons. And as students learn about this one, I have been informed that the S2 level or master level in this lecture. So the carbons, they have 4 types, sp3, sp2, sp, and also quaternary carbons. So this is the general schematic of NMR. Okay, we can see this is a superconducting magnet. In our university, we have 500 megahertz. And in another institute, I found there is around 700 megahertz, but it's very sensitive during that. And we have NMR console that we call NMR brains. Okay, if they are down here, broken, so we have to shut down everything. And also this is the workstations. We send a command to the NMR console, to the brains, and they analyze for us what to do next, what experiment we want. And should have the communication between NMR workstation, NMR console, and superconducting magnets. So this is our NMR setup here. Okay, we have auto sampler here, very nice robots, 24 slots. So it means we can put our samples, key in the data in workstation here, and send our parameter to the consoles. And after that, they start to analyze. Okay. So we have 500 megahertz in our schools. Tend to buy another one, but I'm not sure whether the budget is permitted or not. So I just touch a little bit about simple, which is not teach in lectures. The first one is the sample preparations. Usually we need around less than 20 milligrams, because if we have more 20 milligrams, they will reflect our quality of NMR spectra. Okay, I will show you after this why. So the selection of NMR2 is very important. Okay, usually what we use in our lab is 5 mm diameters, but we have another types which is 5 to 3 mm diameters, because if we have a very small amount of compounds, because we have to prepare the sample in more concentrated forms. So because we need to have a very beautiful NMR. So we have also 1.7 NMR millimeters diameters, but this only if we use micro probes, the small probes, which is 1.7 mm diameters. And this is very, some operators is reluctant to use 1.7 because they have to change the probes. It's quite tedious process. I think it take around 3 hours to do that, because we take out the probes and we install the new probes, and we have to calibrate several times. Okay, so next one is the Shigemi tubes. I think Prof. Unang know about this one very much, because Shigemi tube is famous, originally is famous in Joule model, previously coming from Japan. So they have 2 tubes, and we have to align together and put a small amount of compounds and so on. But this tube is very expensive. I think thousands for one tubes, only for one solvents. If you buy for CDCl3, it's quite cheaper compared to acetone D or DMSOD. Okay, so the third one is selections of deuterated solvent and reference. This is very important. If you choose the very good solvents, usually what we use is CDCl3. If you use rather than this, you have to consider the price and the reference peak for that one, and also the solubility. So usually what we use is a deuterated solvent, because CDCl3 is it's the cheapest one compared to the acetone D. For example, 100 CDCl3 is around cost 500 ringgit Malaysia. So for 25 ml methanol D is cost around 600 ringgit Malaysia. So now the last one is the solvent levels. Usually I told my students to prepare only the height of solvents in NMR tube is around 4 centimeters. It's enough for the probe and magnetic field to bombard during the measurements. But if you put more than 4 centimeters, first you have to consider about the cost, because we have to pay more for the CDCl3 or deuterated solvent. The second one is solvent is diluted. So if the solvent is diluted, you need more time for measurements. Okay, this is the NMR tube that we use, 5 NMR, 5 mm NMR tube, screw cap NMR tube. Usually anybody who are doing catalysis, or what I have experienced is we are doing gold catalysis, and we want to observe what's happened to the compound during the reactions. So we put our reactant reagent and gold catalysis. The loading catalysis is easily for us to open from the top, and loading several percentage or millimoles of catalyst and directly run for the NMR, and we can observe it. So emberized NMR tube is usually used for the compound is sensitive with UV. Okay, so for micro bore NMR tube is what I can say is around 1.5 mm to 3 mm NMR tubes. This is the Shigemi tubes. Okay. And this is a 1.7 NMR tube. Very small. It's very tedious, very difficult to put the samples, but it's possible. So this is the brand that we are usually and advisable for the students to use as Norel, Wilmot, Pyrex, Brooker, and Durance. But the Norel is the famous one, but it's quite expensive. Okay. So for the deuterated solvents, there's a lot in the market, but usually we are using from Merck, Cross, and also Sigma. This is the common one, but Alpha is also you can buy it. Okay. Reference standards is TMS. Usually they assure it's around 0 ppm. This is very important because sometimes if our sample is overlaps, the signal overlap with the CDCl3, for example, especially in aromatic regions, so it's good to have this tetramethylsilane TMS. We just put a few drops in these bottles, and we can use quite a long time. Okay, because if you want to buy the CDCl3 already have tetramethylsilanes, it will cost very expensive. Okay, so this is NMR solvent chat data. So I think I already provide this information to Prof. Unang to distribute among the students. Anybody who are doing the research, I'm not sure for the S2 level in UNPAD, if you have some mini project, for example, for NMR reading the NMR data, you need this NMR solvent chat, because I already advised my student to have at least one from their own during the NMR analysis. So this is I'm preparing the video for NMR operations. I think I can play it. So today we will start to prepare the NMR samples. This is the pure sample that I get from nature product, which is specifically recipe. And what we have to do is make sure you have a lot of the solvent. So you have to transfer some of the samples into the small vial, and after that dissolve in a lot of transfer the drops of this one bar. Try to make sure to dissolve the samples. This is the sample should be light, no cloudy, and precipitate. And after that, have to transfer to the NMR tube. Here we have a 5 mm NMR tube, and transfer all the sample that we have in small bar.
is one. It's this one. So it's going to be integrated on that. So we have to save this spectrum. And finally, we have the picking. So save. And this is how it's looked for. Okay, thank you very much. Bye-bye.
Okay, this is the process how we measure the NMR. This is only for proton NMR. If we have carbon, for example, it will take quite a long time. It's depend on the concentration of samples. So so for the running of NMR experiments, it's depend on gyromagnetic ratio. For example, if the ratio is different, that's why if we have 400 megahertz, it's for carbon is 100 megahertz only. So usually the number of scans, you can put any number, can divide by 4. This is the common experiment that we have, and we can run in our NMR. If you have special requests, for example, anybody who are doing hydrogen storage, for example, you want to measure with aluminiums, nitrogens, and also borons, we can do it so. So for NMR result processing that we usually use, what I think Prof. Unang's teams have already top spins NMR softwares, and also Delta is usually for joules. There are third-party softwares that we are using NMR notebooks, ACD Labs, and MNOVA NMR. So the thing that we will learn after this about the integrations, pickings, phase correction, this is what we have to do it. And also if the axis is quite not really fit what you expected, so you have to do some calibrations to it's really to the NMR processing. So this is an example once. If you get this kind of spectrums, what we can expect is if they have two concentrated samples, usually you will get this kind of solvents, this kind of spectra. So what you have to do is at the same time, for example, if you are doing column chromatography and you're not drying very well, so you will get some solvents peak here. So I believe this is the peak of ethyl acetate. So this one and another overlap this one. So if you have hexanes also, you can find the peak is aliphatic regions. Okay. The example number 2. Okay, if you have problem with log and shims, this one if you run without consider the log and shim of the NMR. So what you have to do, you have to run again. After you run again, you will get a very nice spectrum. Okay, this only happen if small quantity. So this is what you have to do. You have to make sure the log is around 500 megahertz and the shim is very nice during that time. So if it's happened, you have to ask your operators or engineers to calibrate again with the reference solvents, and after that run again the samples. Example number 3, this is almost happens when I'm this is several times happen if the sample is very minor quantity, so it's mean the number of scan is not enough. Okay, so what you have is 14 hours. This experiment we run for 14 hours. What we have to do, we have to rerun again the experiments, prolong the experiment maybe for 24 hours, and after that we will see the difference. Okay, so for the part number 2, what we can see is about 1D and 2D NMR. Okay, for the 1D NMR, usually we are referred as a proton NMR and also to carbon NMR. So for NMR, they have you will see this kind of spectra. There is a downfield directions in to the 10 and upfield directions, and of course you have the KMS values. The chemical shifts, usually what we measure is between 0 to 15 ppm. Okay. So this for the information in NMR, what we can get, there are 4 information there. The first one is number of signals, which is indicate the number of different types of hydrogen in molecules. The second one, the position of the signals, indicate the types of hydrogen with molecule contains. If they have heteroatom, they are going to the shifted to the right, to the left. Okay. So for example, CH3 signals is different with OCH3 signals, for example. So the third one is intensity of signals. Okay, we can indicate the relative amounts or how many protons in the molecules by doing the integrations. The fourth one is a spin-spin splitting signals, give the further informations of the neighboring environment for the various hydrogen in molecule. For example, they will see doublets, so it's mean they are coupling with another hydrogen. So if they have singlets, they have no coupling with the neighboring protons. This is a kind of examples. This is the general characteristic of chemical shift. Okay, for example, for the alkyls CH3, for example, the region is 0.9 to 2. Okay, and also for alkyne is 2.5 ppm. If you have heteroatom, it's shifted to 2.5 to 4 ppm. If you have alkenes, it's 4.5 to 6 ppm. The aromatic regions, which is what we will touch after this, is around 6.5 to 8 ppm, because some students, what I can say, they expected to have aromatic, but they are doing high field. But this is wrong in terms of the theory. Okay, if you have carbonyl, especially aldehydes, the region is between 9 to 10. This information should be in your mind. So it will guide you how to predict the compounds easily. Okay, this is another region for NMR spectrum. So this is the region for the downfield. This is the upfield. So similar that we have table before. So this is what you have, what should have in your mind. So this is the common splitting pattern. For example, if you have a doublets, for example, the adjacents, it means they have another protons. If you have triplets, they have just it could be a CH2. Okay, this is a very simple and basic understanding about the NMRs. If you have quartets and triplets, the shape of the compound will be like this, and quartet and also doublets should be also like this. This is the commons that we have. More than that, triplet, doublet, triplet is commons. More than that, usually septets, for example, heptets, usually we declare as a multiplets. Okay. So for the carbon NMR, okay. So for NMR, as I said, we have two information. First one is carbon, the second one is a proton, but we will touch about the carbon now. So the carbon are easier to analyze that proton NMR because the signal is not splitting. It means they are not decouples. So if you receive the NMR, carbon NMR like proton NMR, you have to run again the experiment and ask the operator make sure the bus program is a decoupled setting. So otherwise you will headache also because they are coupled with the neighboring carbons. Okay. So for example, we can see the carbonyl and the carboxylic acids, the carbonyl groups is around 179, for example. This CH3 is around 21 ppm. Okay. So each type of carbon appear as a single peak. It's helped us a lot. At least, for example, if you get the compounds, if you are doing natural products and you have the compounds 10 carbon, for examples, and based on literature, they show that compound is terpenes compounds. So you can get, oh, this one is a monoterpenes. If you have 15 carbons, there is a sesquiterpenes. If you have 30 carbons, usually is a triterpenes. Okay. So this is the chart that explains the distribution of the functional groups, for examples. Okay, if you have double bond, the region is between 100 ppm to 131, 40, something like that. Because if we include the quaternary carbons, if you have the aldehyde. The ketones is around 169, for examples. If you have ketones, independent ketones, this is the carbonyl groups, and ketones, the range is between 100. Usually is 200 above, usually for the ketones, okay? For the 2D NMR, okay, we already learned about one H NMR, carbon NMR, but for the 2D, usually what we use is a quasi NMR. We can see the correlations between neighboring proton. This is the correlation between neighboring protons here. Okay, this OH can see this proton, and this hydrogen can see this CH3. This means the correlation between carbon. What I can see for myself is only proton-proton interactions. For the depth, it's usually explained about it's a 1D experiment. It explains about the types of the carbons. We have 4 types, okay, methane, methylene, and also quaternary carbons, and and CH carbons. So this is depend on the hybridizations, okay. So for the HHQC, or previously we called HMQC, HHQC is the new one, HMQC is the previous ones. Usually we can see the correlations between proton and their own carbons, okay? Only that, okay? This is very good information. Okay. For the HMBC, we can see the correlations between proton and their neighboring carbon. They have 2 types of correlations. The first one is J2 correlations, and the next type is a J3 correlation. Maybe after this, I will show example about this one. Okay. So for the part 3, it's quite fast, I think, because I have 2 hours only for the lectures. Okay. So application NMR in organic synthesis. What we can use NMR in organic synthesis. The first one what we can use is to determine the product reactions. Okay, we can use, for example, 1D and 2D NMR to determine the products and assign the skeletal of the compound. This is the common one. Okay, we do reactions in organic chemistry in one vessels, and after that isolate and so on, and we do this kind of reactions. The second one, is predict the product formation. For examples, okay, you are very lazy to do TLC, okay. So during that time, just doing for example, reductions for transformation of ketone to alcohols. So what you have to do is you just take some of the reactions, run the carbons in concentrated manner. So, and after that, run the carbon, you can see the disappearance of ketone around 200 ppm. It means your reaction is finished. This is just like that, okay? For the third one, you can determine the ratio of mixture, okay? For examples, you are doing very new chemistry, for examples, and after that, the funny thing is, you are doing several column chromatography, and you cannot separate the compounds. Okay, in one, there is one spot there. So what you have to do, you cannot separate, you don't have HPLC. And what you have to do, you have to report in the mixture. I have a few examples after this, which is published last year's about this one. We spent a lot of effort to do column chromatography, and after that, what we realized, we cannot do that. Okay, the last one is calculation of percentage of transformations. We can do it by doing the integration and the ratio of the compounds. So the first one is a normal ones, similar like natural product, and the second one is prediction of the products. For examples, we want to change, we want to do the Wittig reactions, okay? So and also with iteration, we want to produce some alkenes in these functional groups. What you have to do is you just take some of your reactions and doing NMR, proton NMR. What you can observe, there are, we know this one is around, the signal is around 9 ppm. Okay, it's around these regions, and suddenly it's disappear and form a new peaks. Okay, for these two germinal signals is represented with these couplings. So it's mean, okay, I'm finished. I just want to do walk up, go for it. Okay, this is the solvent that we use during the reactions. Okay, this is the first examples. Okay, same goes here. If you want to do this kind of chemistry, you can see this difference of signals. Okay, for determine the ratio of measure, okay, as I said, this is a problem that we face quite long, I think several months to solve this one. So what we observe, this kind of hack reactions will give you two products. The first product is the difference is the location of double bond here and double bond here. Okay, during the mechanism studies, we observed during the last stage of the late stage of eliminations, which is beta-syn eliminations, they have two possibilities to do some elimination, which is in these positions and these positions, and we get these two NMR. And we expand in this region, what we observe is they have two sets of signals. This is the first set, including this one, and this one is the second set. Okay, the rest we cannot difference. For this one, we can easily difference double here. Okay, so what we can do is we take a ratio, the integration ratio here, and we can make the ratio for the both compound. In this reaction, if I'm not mistaken, is around 1-to-1 ratio. It means 50% of compound A and 50% of compound B. Okay, this is example number 4. Okay, we want to do a reduction for examples. We can see that this OH peak is represented in these regions. Same goes to the carbons. We can see usually for the carbonyl groups is usually around 200 ppm. There are no signals appear in 200 ppm anymore after we run for the carbons, and so it's mean they are 100% transformations. This is experiment number 6. Okay, we will discuss about this one later. So because this is related with our examples, what we want to discuss. Okay, so we will do some hands-on training on NMR in organic synthesis. I believe I already give some spectra to Prof. Unang. So, and I hope you get it, you print it, we can do it together. So again, what I'm using to step-by-step analysis NMR. First, you have proton NMR, you do some simple analysis what functional group exists, for example, based on the diagram that we discussed previously. So, and after that, we are doing carbon NMR by doing numbering of the carbons. Okay, so, and after that, we have carbon, you have to align with depth 135. Okay, they have 2 more depths about this one. So, but usually what we use, we run first depth 135. If we cannot get any informations here, so we have to run depth 45, depth 19, for example. And this depth 135 is comparing with CH3, CH2, CH, and C quaternary. And after that, after we get the carbon informations, we are doing HSQC analysis to determine 1H signals. And after that, we have to, all information from 1H signals, we transfer to proton NMR, and after that, quasi NMR, HMBC. And if you have very big compounds and that compound have the chiral centers, I'm strongly advise you to run 2D noisy correlations, or you can request Roisy. Roisy experiments is the combinations between noisy and also quasi experiments. Okay. So what I say here about the HSQC and HMBC, okay. So HSQC usually measure the J1 coupling. It means their proton and their carbon. This is the J1 coupling for HSQC or HMQC. For the J2 coupling, they measure proton can see the neighbor carbons. Okay, this is the J2 couplings, usually for HMBC. Okay, 1 and 2. Okay, this is what I say about J2 coupling. Is the 1, and this is number 2. Okay, for the J3 coupling, which is number J3 coupling, which is number the color blue color, is a J3 coupling, usually HMBC. We can see this proton can see this carbon. Okay, it's a 1, 2, and 3. Okay, and this proton also, if we draw in 2D orientations, this proton can see this carbon 1, okay, 1, 2, and 3. HMBC, if we have some connectivities among the functional groups, HMBC is very important to determine and locate the substitution.
Pemberitahuan aku gempa mulu dari kemarin.
So
Nggak tahu di mana.
this the operation J1, J2, or J3. So for the NMR training, what I already give to you is this kind of spectra. Okay, I'm not sure you all can see or not. Okay, this kind of spectra. So this experiment is the head coupling experiment between this styrene and also this amide precursor. So we are doing in palladium chemistry and we get this kind of compound. I'm not sure we have enough time to discuss, but I will try my best to do so because I want to touch a little bit about the proton and the natural products. Okay. What's happened? Okay, anybody who loves to do organic synthesis, you have to understand the mechanism, of course. Okay, in Heck mechanism, there are involved four steps, which is starting with oxidative additions. Okay, and also followed by syn insertion carbopyrrolidexations. Okay, because the combinations between palladiums involved in this interchange, and followed by CC internal rotations. They are rotates the bonds, and lastly, it's involved beta hydride eliminations. In last stage, this is very important. The last stage in beta hydride eliminations, during that time they have several positions that they can do. Okay, so they have one beta hydride, second beta hydrides. Okay, and there's another beta hydrides. First, they have three probability to produce the compound. The first one is the trans, which is the vicinal one, trans orientations. The second one is the vicinal, also the cis orientations, and the last one is the geminals. Okay, based on our experience, three types of compound is possible to synthesize, but in the end, it's depend on the product that you manage to isolate. Okay, because from here you can see the different patterns of the carbons coupling. So for example, you can see this proton coupling with these protons, but the J coupling values typically is around 16 megahertz, 16 hertz. Meanwhile, for the vicinals, you can see 9 to 10 hertz, but the geminals, you can see the different patterns of the NMR. Okay, so because the coupling is this one, you can see two types of doublets. Wait, my computer is hang now. So let me check. Okay. Okay. So another way that you can do for anybody who will learn to do synthesis, what you have to do if you don't have any idea what compound you get, what you can do is you can overlay all the starting materials. This is the products that you get, you assume to get, okay? And after that, you put together your starting materials. This is the styrene and this is the amide precursor. And after that, when you get the pure compound, you can easily assign this. Okay, for example, this peak to peak is represented in these regions, for example. So for this region is already assigned for the protons. Okay, you can see this peak is the sepia for these protons, for these these positions. So it's mean the reaction happens. So you have to do more about this one. Okay, so and this one, what you can see here, this is the aromatic regions. Okay, this is the aromatic regions. Maybe I can open my tab for one. Okay, let me try. Okay. Okay, this is the aromatic regions. Usually what we can use, this is the aromatic. Okay, this is the aliphatic regions usually. Okay, so if you see this proton and this proton, okay, is represented in these positions because this proton here, okay, coupling with this 2CH3 can give you multiplets, and these doublets, okay, these doublets is represented in these positions because this CH3 coupling with this one is become doublets. Okay, and of course, if we assume this kind of compound, okay, if you calculate the J coupling, you can see these very nice and symmetry shapes in this one. Okay, you can calculate the J coupling. The J couplings is around 16, yes, and you have to calculate after this. Okay, so for example, what next? What information you have? Okay, okay, you have nice triplets here. Okay, triplets, doublets, and doublets. Okay, for triplets, usually in these positions, because okay, if you extend these positions, can see this proton is become doublets, but this proton can see this proton is become triplets. Same goes to here, is become triplets, and this one is become doublets. Okay, this is the general analysis that we can do first. Okay, next, what can we do? Okay, here the NMR. Okay, you have okay, this is if you assume this kind of compounds, what you can have is here is around OCH3. If you have heteroatom, okay, it's shifted to downfield regions. Okay, but you have the two integrations here. It's a OCH3 times 2 is become 6 protons. So the first one, hydrogen, the second set of hydrogen is become 6 hydrogens, and which is these regions. Okay, as I said, this one in these positions is multiplets, this one is singlets, and this one, if you see clearly, is a doublets to represent this. Because they are in symmetry form, it shows only one signals. Okay. But you can see the integration here is 6. It means 2 times CH3, which is 1 and number 2. Okay. Okay, next, if we see clearly, this is the aromatic regions, for examples. Okay, this is the aromatic regions. Okay, you can see this integration is number 1, and this integration is number 2. Well, you can see the aromatic region here. This is proton number 1. This is proton number 2. Okay, both show if you are run your sample in the lower region, I mean 400 megahertz, you will see only singlets. If you run with 500 megahertz, 600 megahertz, there will be a doublets because they are meta couplings. The J couplings between meta couplings is around 1.8 to 2.3, for example. Okay, so this information you should keep in your mind. Okay, so the rest what you can analyze here is this one. If you see clearly, this is the very symmetry proton. Okay. Okay, and you can calculate the J coupling. For example, if we take a calculator here, so I have the calculator in my hand. Where is it now? Okay, take the value here. Okay, 6.9282 minus 6.8961. Times 500 megahertz, if I'm not mistake, it's 16 megahertz, 16 hertz. It's 16.1 hertz. Normally we call 16 hertz. Okay, if we have this one, 7.1157 minus 7.0835 times 500. It's 16 megahertz, 16 hertz also. Okay, so this is the information that we have. Okay, so this is the trans. These two is a trans coupling. I'm sorry, I'm using drawing pattern. That's why it is happen like this. So, and of course, you can see this is the first triplets and the second triplets. Okay, this is CDCl3. Okay, this is the broad signals. Okay, this is a broad singlets, which is usually referred as NH in these positions. Okay, so any compound have SH, NH, OH. You can see the broad signals, but that compound is led by protons. Sometimes they come moving around. Okay, in this case, NH, it's around, I think it's around 7.2223 ppm. So, but you have to expand and look it one by one. Okay, so the rest you have another triplets here, doublets, which is for the second aromatic ring. Naming is A, and this one is B. Okay, we already have all information that we have, so we are very happy for this. Okay, so next what we have to do is you have to label the carbons. Okay, so we will do one by one about this one. I think we have a time, I think, but I'm not sure. Okay, first I think I will change. I will open another software. I hope I still have a time, but I'm not really sure. Let me check. I think this software is not responsive, so it's okay. I will using this slide. Don't worry. It's usually happens. Okay. So for examples, we have this one. As I said, first what we have to do is we analyze all the compounds that we have here. Okay, by using proton NMR. The second one, what you have to do is you have to label all the carbon that exists. Okay, so what we can do is, okay, we can label all the. Okay, so we have to label all the compound that exist. Okay, so we put number 1, number 2, number 3. All peak that you see sometimes is contain the impurities. What you can do, just numbering all the peak that you see, and after that we will see and look again whether that peak is impurities or your signals. So you put number 1, number 2, number 3, this one number 4. Okay, you have to check the table of NMR. Okay, don't numbering this one, because this one is the CDCl3, your solvent that you use. Okay, this is carbon number 5, carbon number 6, carbon number 7. If you expand this one, I think I already provide the expansion of this one. Okay, 7, 8, 9, 10, 11,
Dr. Admi,
Yes.
maybe in the structure there is no number.
Oh, no numbers? Oh, this one. Okay, okay. Later. We will assign later.
Okay, because maybe audience will be confused. Where is number one in this structure?
3. Okay, first you have to labels from your right to your left. Carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. This is what you have to do. Okay. Okay. So second one that you have to do is you have to analyze your depth. Okay. So open your depth. Okay. Open your depth. Again, numbering again. Number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, 17. Okay. Okay, this is the depth depth spectra. Okay, anybody in a positive mode on the upper one, positive. This is the positive. This is the negative. Okay, the positive usually is the CH3, CH. Okay, meanwhile, for the negative is CH2. Okay, in these compounds, there are no CH2. It means it's correct. Okay, so again, this is number 1. Number 2, okay lah. Maybe there's negative. Number 2, we will consider later. Okay, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12. And the peak is not exist in that. Okay, for example, number 12, number 14, yeah, number 14, 15, 16, 17 is C quaternary. Okay, the carbon doesn't have any protons. Okay, so this one is a number 13. Okay. Maybe stop video. Choose. Maybe I have to change the none. Okay, this is my home room. Okay, it's okay. It's better like this because I want to show the tables. Okay, so I hope everybody can follow this one. Okay, I will open the chat box. If I too fast, you can stop me. Okay. Okay, this is cozy. This is SFC. So, okay, again, okay, as I said, first, simple analysis for the proton. Second one, carbon. Third one, simple analysis for the depth. Last one, this one, okay, we proceed with the HSQC. This is the HSQC. HSQC. Open the HSQC signal. No problems. Okay, this is the HSQC. I'm not sure you can see or not. This is the HSQC. Okay, so what you can do is take a rulers. Usually I'm using visualizer, but now we don't have the visualizer because it's not responding in my computer. So what you can do, numbering again the carbon. This is number 1, number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. because the HSQC only show a correlations. I'm using terms of correlations between the carbon that have only the protons. Okay, if we talk about the simple. Okay, so what you have to do is you take a ruler. This is very, I'm not sure it's very good or not. You take a rulers. Okay, and after that, I'm using rulers and my drawing pad. Okay, so it's mean this proton is proton number 1, H1. Okay. Okay, number 2. Okay, here there is some trick. Okay, you can see whether the carbon peak is your compounds or not by see the 2D correlations, whether the HSQC or HMBC. In this case, we already assigned this one is a proton number 1, this carbon number 2 is no. Okay, so we can eliminate. Okay, this is not your peak compounds. Okay, so we exclude number 2. So it's become 1, 3, 4, 5. Okay, so after that, I'm not sure. Hopefully you can follow. Okay. Okay. Actually, it's going up. And after that, okay. So it's proton number 3, H3. Okay. And this one do it for the all carbons and proton correlations. This one is H4. Okay. And this one is H5. This one is H6. And this is very tricky here. So because you have to expand here. So let me try again to open the software visualizer is working or not. Okay, so it's working now. My visualizer is working now. Okay. Let me connect with the visualizer. Okay. Okay, you can see my hand now.
Yes, I see.
Okay, thank you, bro. At least I have some response. Okay, this is a very helpful tools that I bought a visualizer. So what we can see here is you can see the correlations. Okay. Let me expand. Okay, let me stop sharing for a while. I will stop sharing this one. I end the show. Okay, this is visualizers. Okay, so I will expand the visualizers. Okay, the first one, what we have done is we analyze the protons, simple analyzing. And the second one, we do analyze for the carbons, followed by depths, and this one is HSQC. Okay, HSQC, what we can see is the correlations between carbon and protons. Okay, but the way that we can see is the proton can see the carbon. Okay, not carbon see the protons. Okay, for example, this one is proton number 1. After we are using, you can do by yourself, for example. So yeah, just simply put like here, and after that, draw the straight lines and going up. Okay, this is carbon number 3. As I said, for carbon number 2, I think there are impurities or solvents, something like that. So we are eliminate carbon number 2. Okay, this is carbon number 4. Okay, and this is carbon numbers 5 and number 6. It's very helpful informations for the aromatic regions, and this is very challenging. So what you have to do, you have to expand these regions. Okay, expand these regions. Oh, where is it now? Okay, you have to expand this region. It's become like this. Okay, and you have to see clearly the correlations. Okay, the most challenging part is to determine which one is number 7 and which one is number 8. But if you see the contour here, okay, number 7 is situated in this position because we have to align in the middle or the center of the contour. Okay, so it's kind of like the heels. Okay, the heels that you can see the contour. You see from the top. Anybody, if you remember when you would study geography, you can see this kind of the name contour. Okay, so this is carbon number 7. Okay, we put number 7 here. Okay, and this one, okay, we already assigned this one, is remaining is become here. Okay, and this one is carbon number 8 for proton number 8. Okay, and after that, this contour is carbon number 9, proton number 9, and lastly number 10 here, and number 11 in these triplets. Okay, if you cannot see the triplet, is like this. Okay, so just playing some drawing here, so you can draw like this. Okay, oh, like this. Okay, this one, of course, refer back your table that I given to you, solvent table. So this one is CdCl3, and this is the broad NH. There are no correlation in NH because this is the carbon, this is the proton. Okay, no NH. If you need the correlation also, you have to run NMR, N15 NMR. Okay, so next 10 done. 11. Okay, this is carbon number 11 here, and this one is quaternary. As I said, 12 quaternary, 13 in this contour, 13, 14, 15, and above is a quaternary also. Okay, I hope it's clear. Okay, students. Lecturers is okay because they are teaching these subjects. Okay, anybody want to respond, just chat with me, it's okay. So you already have these informations. Okay, the first one, you have simple analysis for proton, followed by carbon, depth 135. Okay, after that is HSQC. After HSQC is proton NMR again. You have to transfer all information here and label all the proton that you get. Okay, so open the proton NMR. Where is the proton NMR?
Ask me. May I ask you?
Yes, Professor.
Yeah, there's a signal on the 124 on which correlate with carbon 7 here, which is H13.
Where is it?
124, I think.
Okay, this one.
Yeah.
Okay.
There's a correlation with the C7. Is that the impurities or the
No, it's not impurity.
satellite?
Yeah, it's satellite actually.
Oh, okay.
Sometimes they are reflex. It means the proton and their carbon is nearer between each other.
Okay, so that's
But
this.
it depends on the intensity. If we
Mhm.
talk about the intensity, this proton will be the real protons, the correlation here, and this one will be for this level.
Okay, so that's the satellite, yeah?
Yes, yes.
124.
Yes.
Okay.
Yes,
All
Pavin.
right.
Thank you, Pavin. Okay, so again, okay, open your proton, students. Okay, so yeah, quite messy here. I'm sorry. This is how we read the NMR. Okay, I hope it's can see here. Okay, so for the first arrangements of the COSY, what we can see, this is the COSY one. Okay, first one. Okay, you can start label and transfer all informations from the COSY from the HCC to the protons. Okay, the first one, this is proton number one. Oh, sorry. Okay, this is proton number one. Sorry, again. Okay, this is the proton number one. So you can label H1 here. This one is H3. Okay, maybe there is some water peak around here. It's normal, okay. So because we are humid country, so this one is H number 4. Okay, this one is H number 5 and H number 6. This is quite messy in these regions. So what you have to do is you have to expand this one. Okay, so after we expand, I think I already give you the expansions. My table is quite small, so after the expansions, it's become like this. Okay. Okay, we expand the COSY also. It become like this. Okay, transfer all informations here. Okay, we have 13. Okay, I put here. We have 13, 7, 9 broad singlets for the NH. Okay, we label NH here. CDCl3, 11, 10, and 8. Voila, it's finished. Okay, so we already done all informations here. Okay, we already run general analysis for NMR, carbon 13, DEP 135, SSQC, and proton NMR. Okay, what's next? What you have to do? This is my style. Maybe Prof and also Dr. Rani's technique is quite different, but do whatever you feel comfortable. Okay, I prefer to do this kind of technique because it's helped me a lot. Okay, I provide you this kind of tables, and after that you have to fill all the information here. Okay, so during the proton analysis, what you can do is let me see. Okay, what you can do is, okay, you can do some calculation for the J couplings, for example. Okay, this one is a doublets. Okay, take a calculators. Where is the calculators now? Everything is missing now. Okay, so what you have here is 1.2968. Okay, here minus these values, 1.2835, and after that times 500, because this sample have been run in 500 megahertz. So this one is 6.7 hertz. 6.7 can 6.7. Okay, that's okay. So you can put is okay. Is around 1. Okay, this value is 1.296 1.30. doublets, J coupling here. Okay. Okay. This one, what you have to do is you have to find the center value for this one. This one is center value also. It's around, or you can take a range with this one and this one. It is depend. Okay. So if I want to take a range, is between 2.55 to 2.61. Okay. This one I consider, to make it easy for everybody, I consider as multiplets. Okay. If you want to read, you can read. Okay. So this is 1 hydrogens. Because I can see this 1 hydrogens. This one you can declare as a, I have a erase here, 6 hydrogen. Okay. And these values, okay, these values is 3.82 singlet. Okay, singlets. Okay, singlets. 6 hydrogen from here. If you remember during our undergraduates, okay, we have to calculate manually by using rulers. Okay, so now we have the computer to read for us. So it's better to use computer. Okay, so this is the first one. Second one, okay, this one is actually a doublets. Okay, doublets is look like triplets, actually is doublets. The first one is 6.43 doublets. Okay, so the value is between 6.4300. Wait. 4300 minus 6.4257 times 500. Okay, the first doublet value is 2.1 hertz. The second one, 6.4257 minus 6.4214. 500. Okay. Also 2.2 hertz. Okay, this is 1 proton. Okay, so you have to continue by yourself, okay, and complete the tables. So with the all informations here, what you can do is transfer all informations here. Okay, because we already done that, 135, carbon, proton NMR, and numbering based on the number of carbon. Okay, anybody who have question until these levels? We still have 40 minutes before we finish. Boleh faham? Kita cakap
Any
bahasa.
question for student?
Boleh faham? It's okay if you want to speak bahasa.
Okay.
Bahasa okay, boleh, no problem.
Ada pertanyaan?
Okay, tak apa, Prof. I think they can follow. Don't worry. Okay. So, okay, if you have this one, we already fill this 3 column here. Okay. And after that, what you can do is we go for cozy. Okay, we go for cozy. This is SSQC done, carbon done, cozy. Okay, this is the cozy. Let me arrange. Actually, for my class for NMR, usually it will take half day from the beginner, because this is what I'm doing. For the complex structures, 1 day, because we have to go very slow. So for this class, I'm a little bit fast because I'm not sure I don't have time or not. Okay, I'm really sorry about this.
Okay, never mind. Maybe they already know what about the example.
Okay. Thanks, bro. Thank you. So this is very nice and very beautiful courses. What you can do is, okay, you can do, actually there are no this kind of grid, but I set up in the software. Sometimes it will help you to analyze the samples. What you have to do is, again, you label again the proton number here from 1, 2, we don't have 2 anymore. Okay, number 1 until it's here. Okay, so and after that, put the straight line here. The COSI is kind of like a mirror image. Okay, if you can put like this, so you can see the reflections between two contours. So, okay, let's go. Okay, when you try to solve the structures, you start with the simple area first. In this case, for the simplest area, in this area, not this one. This is very complicated. So what you have to do, mulakan dengan yang senang, okay, and slowly buat yang susah. Okay, so this is very simple areas. So you can see only one. Okay, make sure the straight line touch this particular layer lines. Do some reflections. So this means this contour is a reflection of this contour. And after that, we can see H3 is near to sebelah. H3 is bersebelahan dengan H1. Okay, this is the first one. The first information that you have. H3 is near to, beside to, okay, H1. Okay, this is the first information. Okay, and after that, there are no correlations here. Okay, no correlations. And after that, you have to focus in this region. What you have to do, expand, enlarge. Okay, so this is after we expand, enlarge. Okay, that's why you need some, if you have a pure compound, you are lucky. If you don't have the pure compound, at least you can read some information. Okay, if you measure quite long, it's become like this. Okay, because that's why we have to try and errors. Okay, to get the perfect spectra, I think it's almost impossible. But you can try. Don't worry. Okay, what you have to do is, what you can do is, okay, so you can see the correlations going down the straight line. Okay, and after that, it's connected with the H11 here. Okay, so it's mean like this contour is a reflection of this contour. So you can put H8, can see H11. Okay, okay. Same goes to this one. Okay, you can see H10, can see H11 is a reflection from here to here. And this one, H10, can see H9. Okay, right now you are pull all information first, okay? And after that, H11, this is very big square shapes. So this is the reflection of this one. So H11 can see H9. Okay, we move to here. H7 can see H13. Okay, so in this one, H6 can see H5. Yeah, probably yes. Okay, probably yes. So we will do some probability. The thing that not really good for the NMR, if you use higher frequency, okay, sometimes they can jump to another neighborhood. Okay, that's why sometimes we can see, instead of neighboring protons, they can see another neighboring proton. For examples like this H. Okay, so sometimes they can see this. Okay, that's why if you have 400 megahertz, it's good enough. Okay, okay. Normally we can see only this proton. The theory. So sometimes you can see also this proton is depend on the nature of your compound. Sometimes we call Jacob-Delbeny coupling, for example, sometimes. Okay, so you have to be prepared. Okay, that's why anybody who are doing protein chemistry, they love to use a high magnetic field because they can see the sequence. Okay, so this is the COSY informations. All information is here. So what you can do is transfer all information in this table for the COSY. Okay, because in the end, you doesn't need to read all spectra, but by using these informations, you can see the correlations. Okay, so COSY done. Okay, first COSY done. So the last one what we have to check is the HMBC correlations. HMBC correlations. Okay, this is the HMBC correlations. Let me check how many spectra I got here. Okay, this is the last one, HMBC correlations. Similar like HSBC, but HMBC, okay, this is HMBC. HMBC correlation between proton, not their carbons, but their neighboring carbons. Okay, oh sorry. They have J1, J2, and they have J3. J3 quotient. Sometimes J4, but it's depend on the nature of your compounds. Okay. If you get this very messy spectra, what you have to do is find the good area to solve. Okay, the first one, if you get this one, this spectra, the good area that you can do some connections is in this area. Okay, this area is not messy. Okay, this area is not messy, and also this area. This area is not messy. Sometimes maybe this can consider also. Okay. Okay. Okay, we start with this one. Okay, the 17. Okay, the 17. Okay, do like this. Don't forget label 1, 3, 4, 5, 6 by using the proton that we have and also the carbon that we have. Okay, I'm waiting any reply from students. Okay, so what you have to do is join the contour. Okay, this proton number 1 can see it's normal. Can see their own carbon, so I'm ignore that one. Okay, so carbon number 1 can see proton number 3. So proton number 3 can see carbon number 1. Okay, and of course, if they can see each other, okay, proton number 1 can see carbon number 3. Okay, so if you see this kind of 2 dot here and the straight line, okay, for example, like this, okay, usually you can see the correlation in J1. Okay, it's mean, okay, it's di tengah-tengah di sini, okay, sama macam ni, similar like this. Proton number 4 can see carbon number 4, but sometimes it happens, sometimes it's not. Okay, I hope it's clear. Okay, so this is done. We move to the bottom one. Okay, 17. Okay, we see proton number 3 can see carbon number 17. Okay, proton number 1 can see carbon 17. The rest, no. Okay, what we can see is, okay, okay. Next, what we can do is carbon number 16. 16 can see proton number 6. Carbon number 5 can see proton number 5 can see carbon 16. Okay. Number 4 can see carbon 16. Okay. Again, next, find the simplest one. Okay. This one is CDCl3, CDCl3. Okay, this one is also CDCl3. It's mean center of this one. Okay. Next, okay, what we can do is proton 6 can see carbon number 5 for this one. Okay, carbon number proton number 13, carbon number 6. Proton number 5 can see carbon number 6. And as you have to expand it. So I already provide you the expand. Okay, this one is already solved. Okay, so you have to check if this one. Can see carbon 15, H13 can see carbon 15. Okay, and I think you can do by yourself these regions. Okay, do it slowly, don't worry. Okay, as I said, we need more time to read this one. Okay, for examples, if you okay, after you get all informations here, okay, you transfer all information in these tables. Okay, which is already make it from the previous class with my student. Okay, okay. This is next what you have to do. We will do some correlations with this information. Okay, next. Okay, I already give you this information. These informations. Okay, so in carbons, okay, if you refer the table that we studied before, okay, we know this one is a carbonyl. So this is the keywords, the carbonyl. Okay, so we know this one is carbon number 17. Based on this one is carbon number 17. So write down 17 here. Okay. Carbon number 17. Okay, what's next? You have informations here. You have OCH3. OCH3 is carbon proton number 4. If I'm mistaken. I have to find the proton. Oh yeah, okay. So okay, this one is OCH3, proton number 4. So you have number 4 here, number 4 here. Okay, you have the value of NH with the broad signals, which is I have to find this one for the NH. Okay, so what else? You have these 2 trans. Okay. Okay. You can try to put 7 here. Okay, and this one is 13, maybe. Okay. Or you can put 13 here, 7 here. But this one will determine by HMBC correlations later. Okay, we put all information that we have. Okay, we have the aliphatic regions. We have this one, doublets. Okay, doublets. We have doublets here, so you can put number 1, number 1. You have multiplets here, number 3. We are like playing puzzles. And the aromatic regions here, we have 1 and 2. This is this chemical environment is similar, so we can put 6 here. Yeah. We can put 6 here, and we can put 5. Okay, we have done. Okay, so we want to determine, okay, whether this one is, okay, okay, we want to put 7, 3, 13, 7, 13, 7, 13, or this one is 13, 7. Okay, this one we can determine based on the HMBC correlations. What HMBC correlations here? So we have a proton here. Okay. Which proton can see this? Which carbon? Okay, so 13, for example, can see carbon number. Carbon number. Okay. Based on my tables here, okay, what we can see, carbon 13 can see, okay, okay, see, HMBC correlations, proton number 13 can see C6. So proton number 13, okay, this one is absolutely 13, so we can assign the correct one. This is carbon number 13, can see carbon number 6 here, this one. Okay, this is J3 correlations. Why we call J3 correlations? Because this one. Okay. 1, 2, 3. Okay. 1, 2, 3. Okay. This is the J3 correlation. Okay, we have done this one. Okay, next. From the COSY, we can see 13 is neighboring with 7. COSY. 13. Okay. 13 is neighboring with 7. So this one is number 7. Yeah. Okay, so what else? What we have done? Okay, so okay, we put label. Carbon number 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. Carbon number 1 done. Carbon number 3, yes. Carbon number 4, yes. Number 5, yes. Number 6, yes. Number 7, yes. 8, no. 13, yes. 17, yes. Okay, we still have remaining 8 carbon. So what's next? How I can determine this one is 1 and this one number 3? So the first one is a COSY spectra. So we will see the COSY. Okay, in COSY, if you remember the COSY, if you, I can see where I can find the COSY. Okay, in the COSY, if you remember here, H1 can see H3. So H1 can see H3. I don't have any highlighter, I'm using red. Okay, H1 can see H3. This means this proton can see these 3 proton neighboring, including this one. Okay, so they can use neighbor. Okay, so this one is COSY. Okay, so it's done. 1, 3, 1, confirm. Okay. Next, how we know the location is 3 in 17? Check again the HMBC or the table that you have. Okay, HMBC. Let me find the HMBC. I will show you the correlations. Okay, if you see clearly the HMBC, you can see H3 can see H17. H3 can see H17. H3 can see carbon 17. I'm sorry. It's correlation between proton and carbon. Okay, this is number 1. Okay, I'm using this correlations. Okay, and H1 can see 17. H1 can see 17. This one is J3. Okay, if we draw here, okay. Okay, this one is J3. This one is J3. This one is J2. Okay. We already done this one. And we already done for this region. Okay. So next, what we have to do is we have to see the 7 can see which proton which is doublets. Okay, this one is put again H. Okay, we know this proton we coupling with this one is become doublets. This one will become triplet. This one is become triplet, and this one will become doublet. But we have a problem. We have 2 sets of doublets and 2 sets of triplets. So which one? So what you have to do is you have to find a correlation between this proton and this carbon, or this proton and this carbon, vice versa. So what you can see is, okay, 7, H7, based on this table, okay, H7, can see this aromatic is doublets. Okay. Okay, we can from HMBC we can see carbon, okay, proton number 10, which is doublet. Yeah, okay, doublets. Okay, proton number 10, which is doublets. Can see, okay, we can put just using pencil, just put proton number 10. Can see the carbon number 7. So I'll just try an error. 1, 2, and 3. Yes, okay. So this one is J3. It's answering. Okay, which one another doublets? Okay, another doublets is number 8, maybe. Number 8, right? Yeah, number 8 is doublet. Yeah, okay. So this one is carbon number 8. Like playing puzzles. So what you have? We already solved number 10 and number 8. Number 10 and number 8. Okay, nice. Now what's next? Okay, check the cozy. Okay. Okay, so based on cozy, we can see the correlation between H10 and 11. So if we put 11 here, it makes sense because it's correlations between 2 protons. Okay, H11 done. And the last one triplet is number 9. Number 9 here. Okay, so number 12, if I'm not mistaken, is C quaternary. And 14 around here is quaternary, which is you can do after this. And see quaternary. Okay, I hope it will help you. Okay, to find, for example, to find the connectivity between the first. Okay, for example, I'm naming this one is A, and this one is B. Okay, A and B by using alkene bridge here. So you have to use this one is HMBC. And you use this also as HMBC. Okay, inside the system, what you can use is, for example, like this one, you can use COSI. Okay, and for this one, of course, you have to use HMBC plus COSI. Okay, don't afraid if you get very complicated structures, try your best. Okay, I hope this is finished, I think, for structural determinations for this kind of synthesis compounds. And anybody who have questions, I love to answer. Okay, so before we finish, I want to show a few things and give you some idea about what we can do for the natural products. And I have a few slides more. Sorry, Prof, I have a few slides.
It's very cute, very cute.
Yeah, let me jump to the natural product a little bit, because I want to introduce about a few techniques to do that. Okay. So for the nature products, it's very interesting if you are doing nature products, because you learn many things in terms of NMR. I believe Pak Pinos, Prof. Unang, I learned a lot from both of them, and also the team from UNPAD about the specifically for the tritopene compounds. It's very complicated for me personally. So okay, first what you have to do, anybody who are doing nature products, what you have to do thoroughly literature reviews. Anybody who are from my teams, I ask them to spend 2 weeks or 1 month to do some literature reviews and come up with the ideas, what the common compound that have been isolated. For examples, every compound have this very special biosynthesis. For examples, anybody who are from COPSIA, which is my student are doing now, is indoles, alkaloids, but they have, I think, more than 10 types of iburnins, aspidofractanins, skeletons, okay, from Meliaceae species, which is I think Prof. Unang doing now, is terpenes. They have a lot of triterpenes, terpenes, tetraterpenes, and etc., and including the derivatizations of terpenes, which is laminoids. And if you are working on adenine in this media, normally is working on lignin, neolignins, and then the acids, which is we are doing now. For LCO Daphne species, isoquinolene or soquinolene, bisbenzylquinolene, and etc. And for Diospiro species, what I think Pak Pinus are doing that now. So usually we can find the lupin, ursin, or olean skeletons, which is very nice, but quite complicated to read. Okay. So for example, for the COPSIA species, this is iburnine skeletons, what we have. Okay. So we can see this is the crude extract. After doing some acid-base extractions, we can find, okay, we can find now already the pure from the extract. Also, we can see the iburnine skeletons. This is a cobaltamine. It's not a iburnine skeletons, but it's different skeletons. But this is iburnamines, larutensin. The difference is in this ring. Okay, this is another ring. Instead of 5 ring, 1, 2, 3, 4, 5, they have 6 ring with these functional groups. And after that, iburnamino is the cleavage of the larutensin. Okay, so this is very interesting. If you are doing nature product, astaghfirullahaladzim, it's very so many things that you can explore. So another example, if you are working on terpenes, for example, the Diospiro species, you can find the lupiol, lupinone. The different is only the functional group in this, I think, A rings. Okay, instead of OH, they are using ketones. And after that, the butylene, the derivatization of this ring. by converting CH3 to CH2OH. And beta cytosterol is the steroid groups, and diazoxide is the cis-quiterpene. This is very interesting and very, I don't know what to say, nice compounds to explore. But lupinol and butylene, is so many publications about this one, but I think we have to do some derivatizations. So this is my main PhD projects. For example, we have kingianin A, kingianin SA, sanguinolin B, for examples. This is very interesting compound. Now we are exploring the new plants for this one. We found and we expected to publish within this year, inshallah. So there are so many techniques in the world that you can explore. The first one where you can do, if you heard about the metabolomics, omics, proteomics, omics, something like that. So you can do that, but the problem is you need a very good instrument to do that. For example, the metabolomics, and if you have a lot of money, you can do that. So okay, so nowadays that I can heard is that they are doing multivariate analysis, but I'm not sure in detail about this one. But it's good to explore, but you have to balance about the chemistry that you have do now with the new techniques. So for example, during my PhD, I'm doing NMR hunting methods. So NMR guided. So it means every fraction I have been isolated, I run the proton NMR. So we can see, for example, fraction B here. So we can see it's contain kingianin A skeletons, because we can see this alkene functional group, which is situated in this carbon number 3 and 4, and this is 6 to 5, maybe 8 to 7 here. So this double bond and this NH, which is a triplet signals. And if we see the fraction number A here, we can see clearly the enryandic acid skeletons by comparing the substitutions. So it's mean you have to do more column chromatography to get the pure compounds, but at least you are really confident that inside your spectrums or your compounds or your fractions have this kind of compounds. Okay, so because this one I isolate as a major compound, this 3, so I'm continue hunting the compounds. For this one, I get for this project I get 10 new compounds for and then the acid series, and 3 new compounds for the kingianin Z. And this project, I think during my PhD, I finished in 9 months. It's very fast. But you have to be friend with NMR, because sometimes the operator doesn't need to run your NMR because your sample is quite huge in terms of number. But if you can touch the NMR, you can learn NMR by yourself. It's kind of advantage. So I just want to share a few things about the recent finding. The first one is NMR database. It's very useful database that you can get. It's open access. The first one is the Lotus database. It's a compilation of all chemical isolates in the world, specifically in natural products. So you can try to explore and find. For example, you can search by species and it will come out with the series of your compounds. So this is what I'm doing. I send a sample for HRMS, and after that, the structure that my students propose is not fit with the HRMS data. So I ask my student to refer to Lotus database. And the second one, NMR Shift DB, is quite old database, but it's very informative. Okay, C-Search and NMR database, and also NMRE data initiative. And this is natural product NMR DBs by Joule. This is very informative informations. I think maybe I can share this. Yeah, this one. Okay, I think I tried to open the Lotus database, but I think they are closed for New Year's. Maybe if you have a time to explore this kind of database, is very helpful. So just type your plant names, and after that you come out with the several, I think hundreds of your compounds. This is the NMR Shift database. You can explore by yourself. For example, I already put the URL data, URL details, so you can explore by yourself. So this one, for examples, you can try to explore one by one. Okay, you can predict carbon 13 and something like that. Okay, for examples. structural verification, and so on. But this information you have to register. You key in how many carbons, how many hydrogens, heteroatom, and so on. You can put the range of your molecular weight of your compounds. And after that, you can they will generate the information to you and send you to your email. That's why then you have to register. And the scope for NMR is having the initiative by another team, but I think it will have a good information about this one. If you have a time, please explore it. Okay. So this NMR data by joules. If you have your compound, for examples, you can easily put the number of compound, carbon, hydrogen, nitrogen, and oxygens. Formula molecular, for examples, because from here you can get this one from the carbon and also protons. Okay, and after that they will come some proposed structures. So the Lotus is the recent one. The Lotus database is the recent one. I think you have to explore this information about this one. Okay, so next slide. I think we have 4 minutes left. I think so. So please, if you have the time, please explore these tools. The tool is not, but you have to read by yourself the NMR data, but it's kind of guide to you about the compound that you can find it. Okay. So for the books, okay, anybody who want to learn the NMR, I recommend to have this kind of book by Pavia. It's really informative. If you need the tables for all of your compounds, proton, carbon, and so on, you can find this book, Structural Determination of Organic Compounds, originally in German, but already translates. I have one copy of that. This one, I have 3 books for this one. So by Wiley, basic 1 and 2 dimensional NMR spectroscopy, you can have this one also, and classic in spectroscopy. Okay. So I try to have, during my sabbatical, we try to have an initiative to form our own database. So I would like to invite Prof. Unan teams and also Prof. Pinus to join in this initiative by providing some NMR data, and after that we can share all information that we have. We want to make open source data and open for public, but we have to control the usage of the data by signing an agreements to all contributors and agree to share all information that we have. It means we are sharing the raw data, and they need a third-party software or the second part, the dual software to run all the raw data that we have. This is what the initiative. I have my own spectra. I think around 100+. So if Prof. Unang and also Prof. Pinus love to join, I'm happy to invite you, and we will do honestly, politely with everybody's all contributors. So I think that's all for today. Thank you very much. Sorry, Prof, I take a lot of time to discuss about this NMR software, and this is my team now. So once 3 of them is already left because finished for the graduations. Now I have I think 10 masters, 6 PhD students now. So excluding the collaborators, I think another 2 master students with the collaborators. Anybody who want to know more about our team, scan the QR codes. All the videos for the column chromatography, TLC, NMR, and so on. How to playing around with the software, top spins, you can observe in our websites. Anybody who need top spin from us, I'm happy to provide. But please email me. Okay, I think that's all for today. Thank you, Prof. So I give it to you, Prof, for the next sessions, maybe.
Thank you so much, Dr. Ajmi, for your interesting and useful lecture. Now we open discussion, maybe from student. Okay, anybody question?
Ada siapa nak tanya?
Intan, please. Intan will maybe will study in your lab next next month maybe.
Okay.
Where is Intan?
Yes, hello, Dr. Azmi.
Yes.
My name is Intan Hawina. I want to have one question. Is possible in proton NMR there have peak not perfectly splitting? If possible, what caused that? Thank you.
I don't clear about the question. Can you repeat again?
Can you
Yes,
ulang lagi, Cok.
Okay, in the proton NMR,
Yeah.
there have a peak not splitting perfectly.
Eating nicely. Okay.
Yes.
Do you want to
Cause
know what's the cause of that? Okay. So there are several cause for that that NMR is not splitting very nice. The first one, if you have impurities in your compound, sometimes it will interact with the signals. The most of the problem is depend on the shim and the lock of the machines. So if you get this kind of problems, you have to run again. But before you run your sample, ask the operators to run your with the standards first, and doing line shape, for example, and calibration several times. And after that, inshallah, you will get the nice spectra. Okay, it's a more the technical part for that. So don't worry too much. If you have, that's why I prefer for students to run the sample by themselves, because they know the quality and what they are hunting for. Okay, Intan?
Okay, thank you.
I answer your question. Thank you.
Okay, any more question from the other students? Not only UNPAD student, but also the other students. Okay.
I love to interact with humans. For
Okay.
2 years, it's make me down because I cannot go anywhere.
I see. From Indonesian Islamic University, from Yogyakarta.
But Pinus, do you want to have a same session like this? Okay.
Yeah. Maybe next.
For example, I perform the reactions to do I need the right NMR for the initial reactant to compare or find a product from database with okay, the database okay, thank you, Aman from USM. I'm not sure. Okay, for these questions, what you have to do, the database I show, this one is only for nature product, not the synthesis. Okay, so for this one, what I can say is from the beginner, from the anyone doesn't have any experience, I'm strongly advise you to run your starting materials or intermediates with the same solvent that you use for your final products, and it will make you easy to compare or overlay. So I hope I answering your question from the beginner for the beginner only. If you are expert enough, it's okay. Okay. Another trick is some website, for example, like a website from Sigma Aldrich or Merck, they are already give you supporting informations regarding the NMR. But the problem is we didn't know what solvent they are run. Okay, you open the Sigma and find the catalog name, click the compounds, and you can see the below one, they have informations whether they have proton NMR or IR. And this is the common practice for the suppliers, the big suppliers, I mean, Merck, Sigma, across, and so on. I hope I answering your questions, Aiman. If you have more question about this one, you can meet me tomorrow at my office. I'm happy to help. Don't worry. I don't have final year student now. Okay. Thank you. Okay.
Aiman, okay.
Questions?
Any question from the other student? Any more question?
It's me, Prof. Unang. Okay. Dr. Arti, excuse me. just now, the purity of sample affect NMR measurement. And how do you know that purity of a sample? Because I see your explain is detail and it's clearly, yeah, it's clear. And but my student have a spectrum, not to the clarity like of you. Would you explain me, please, Dr. Ajmi?
Okay, it's quite challenging if you are doing natural products. One of them is you can see the copper splitting patterns for the proton NMR. If there are, and also the integrations. So if you see the integration is below than 1, by pick any peak that you see you use as a reference. If you see they are below than 1, it's mean they are your impurities or the your compound is not pure. The easiest way that you can do is you can run your sample with carbon first. Okay, if you run your sample with carbon, you can see there are 2 sets of the carbons. The first one is very intense. The second one is less intense or not intense. So it means your compound is not pure. But I think you can still read the NMR by using the HSQC by predicting which carbons have represented with your major compounds. I think this is the way that we use because I think last two Fridays I tried to have one of my colleagues from UC Malaya, and alhamdulillah within three hours we can solve the compounds. Okay, Prof.
Okay, thank you, Dr. Azmi. Thank you, Prof. Unang.
Okay, you're welcome. Okay, any more question? Okay, that Dr. Ajmi, because there is no more question. Okay, maybe I will give us some appreciation for your lecture. Big applause for Dr. Azmi.
Thank you very much.
Thank you, Dr. Azmi.
Ladies and gentlemen, before the close the lecture, I will show the appreciation from our department to Dr. Azmi. Can you stop screen, Dr. Azmi?
Yeah, I already stopped my screen, I guess.
Ready? Okay. Just a moment.